have eaten. I'm still sleepy though. Okay, so. It's exam review day, and no one else is here at the moment. So, do you have any specific questions or inquiries or things you'd like to discuss for the exam?
No, I was just coming because I thought more people would show up and then you would talk about something.
Well, when I tell people that they don't have to come, they usually don't, in my experience. So I was expecting either none or a few. I don't think I was expecting one. This is a little unprecedented.
No, but like there are thinking about I watched the chapters 9 and 10.
Okay.
And I don't get like the word questions that you were talking about coming from those two chapters. Like how would they be like, just like in the test or quiz homework online?
Okay, now, do you remember specific homework questions that you were having trouble with?
Like the what's it called, dispersion.
Ah. Let's see if I can pull up the slideshow. Okay. Oh, no, actually, display. Okay, so let's start with the main. Dispersion is one phenomenon related to specifically the concept of refraction. And as a concept, refraction tells us that when light or sound, any wave really, hits a boundary and it travels into the new object, it will change direction slightly. So, up on the screen we've got, now we see, right now we're in air, and the camera taking these pictures was in air. So the light coming off of the stick or the spoon traveling through air hitting the camera is what we would think to be normal. But light coming from the part under the water has to travel through the water, it hits the edge of the water, and is going to bend as it enters the air. When it bends like that, it sort of has the effect of making it shift where the object appears to be. And it's only shifting where it looks like it is. The object is still where it would normally be. This is still a single conjoined object, and so if you were to put your finger in the actual glass, you would feel it where it's supposed to be. But the light just bent on its way out of the water into the glass. So to draw what happens inside of a prism, light enters the prism, and we've changed mediums. We've gone from air to, say, glass or crystal. And when you do that, it's going to bend and change directions slightly. And it'll do so again as it exits the crystal. because now we've gone back from crystal to air, that's another boundary, it's going to bend again. Now, this is most obvious in a triangular shaped object, in a flat pane of glass like a window, because when the two sides are parallel to one another, the wave will tend to bend back to its original course. So you don't tend to notice this effect when you're looking through a glass window. But this object specifically, we're not just going from air to glass to air, we're going from water to glass to air, up in these pictures. Prisms bend light a lot because they tend to be triangular. And in addition to light bending, we get dispersion from the fact that every color of light bends at a slightly different angle. Every different frequency of light, every different color, bends a slightly different amount when it hits that boundary, only slightly. But so let's say for instance, I'm going to use this picture for this part. I'm going to redraw it here though. The light is going to come in at 90 degrees. And let's say that the red light is going to bend and bounce away at 30 degrees, but the violet light will bounce at 31 degrees. It's a very slight difference, one that you probably would not notice if you were looking at it very closely, or if it was a very small prism. But they do bend, the different colors and different frequencies of light bend enough for this to be noticeable over a large distance. And so what would happen is these rays are going to keep traveling until they hit the edge of the glass again, and now they're going to bend again into air. And as long as the glass is big enough, you will get the effect of the light splitting into the two different colors. So it's just a slight change in the geometry that causes them to get farther apart the larger distance they have to travel, which is one reason why you don't usually notice it in a glass window. The glass window is very thin, and most windows are made of a type of glass that doesn't change the angle too much, because you don't actually want your window to act as a prism. Life would get really weird. But these specific crystals that we call prisms are usually designed and made of a specific material that causes this angle difference to be bigger than it otherwise would be in normal solid glass. And since they're triangular, that causes them to change direction again in a different way upon hitting the other side. So dispersion as a term simply refers to light splitting into its colors because each individual color is going to refract at a slightly different angle. And this effect can be very minor. This effect can also become pretty extreme. Actually, right now, even just with my little visor here, it's not very strong, but when I look up at the lights, it might just be psychosomatic, but I think I see slightly more color in them than I normally would because this is a boundary. So the light will refract through the plastic.
So if it doesn't change the color, it's only refraction, but if it changes the color, it's dispersion.
Well, it's really all refraction. This is a type of refraction. The part of refraction that causes the colors to split is called dispersion, but this is still a piece of refraction. This is a certain thing that refraction can cause. And all of these different colors of light were already present in the original white light. This was made up of every other color, and it's just being, each color is being sent off in a different direction and split. It's not taking white light and multiplying it, it's splitting it down into its component parts.
Can we do some questions from the homework?
Sure.
I had some problems with number 7 on the homework.
Okay, let me pull up some homework questions with numbers in them that are not specific to a single student. Might take a sec. Hope you're doing well today.
I'm good, how are you doing?
Sleepy, but better now that I've eaten. Still thirsty though. The air is getting dry and it's causing problems for everything.
Definitely.
Also, it's cold enough today that I had to actually wear a jacket and pants. What is the deal? I just got used to fall temperatures and now it's winter temperature.
Yeah. South Carolina isn't very forgiving, is it? It just switches on you.
The most consistent thing about our weather is inconsistency.
Yeah.
Okay, so that's number 1. So number 7.
Mm-hmm.
Okay, this is a good question. I've got quite a few about this. This is about Coulomb's law, which is the law that lets us calculate the electric force between two charged objects. I like to abbreviate that as force electric
Right.
equal to K, Q1, Q2, over R squared. So, well, let me minimize the side tab. We have two particles, each with a different amount of charge. So we know their charges, we know how far apart they are, and K is always a freely given constant. K is equal to 8 point, this marker is not very visible. K is equal to 8.99 times 10 9th. So for the first part of the question, you are given everything you need to simply find the force electric. Now, one computer glitch issue that I will admit is a problem here. One charge is negative, one charge is positive. That means that these two charges should attract to one another, and you're going to get a negative answer which indicates this. But the machine is asking for the magnitude of force, which means it wants the positive absolute value of the number. If you include a negative sign, the machine will auto-calculate it as wrong. Thank you, machine learning. But, plug your numbers in, get your force, rip the negative sign off, and that should be good to go. I've also been getting questions with this part. This, we are changing something slightly. We've got two new particles, and they're the same distance apart, so R doesn't change. R is not changing. And we were told that these brand new particles, we don't know what the charge of these two particles is, but we know that they both have the same charge. So when it says Q3, it is listing this as an unknown variable that is separate from Q1 and Q2. We don't know what Q3 is equal to, but we know both particles have that amount of charge. So it's an unknown, but it's an unknown that we have for two different things. we do still know how far apart these particles are, and the problem tells us that these particles are far enough apart and strong enough such that this is the force between them. So we know the force between the particles, and how far apart they are, and K, because we always know K. The issue is just what is the amount of their charge. And they both have the same unknown charge, which means you can plug the same unknown variable in twice. And that should simplify to Q3 squared. So your goal is simply to find Q3. It's just in the equation twice because they both share the same Q value.
So you just have to square the finite absolute V for that then?
Take the square root of.
I mean, yeah. Take the square root. Okay. Honestly, do you mind going over, I was gone like all last week because I was sick. So can you do like a refresher on like, just like a general once over?
On everything?
It doesn't have to be
I'm fine with that, I just want to know, make sure you're.
Everything would be good, yeah.
Okay. Any objections, Nakvi, or is there anything specific you'd like me to cover? Or you just you're just here for whatever's talked about?
Yeah, then maybe talk about wavelength.
Okay. I'll go ahead and do wavelength.
I'm good with,
and
yeah, I'm good with that.
Then we can look at the whole list. Specifically, let's take a look here. Okay. So this is homework question 2 as a specific example for wavelength, really quickly. Wavelength is the physical length of a waveform. If an ocean wave passed you and you can take a tape measure and physically measure how long it is, that is literally its wavelength. Now, the issue is simply where do you hold the tape measurer up to? And the rule for one wavelength is you want to go from one part of a wave to the next iteration of that part. So the distance between these two bottom pieces should be the same distance as the distance between these two top pieces, which is the same as the distance between this rising edge and this rising edge, or this falling edge and this falling edge. So as long as you are very specifically measuring one whole iteration of the wave, one cycle from a spot back up to that spot, the distance between those 2 points is the physical length of the wave. And every wave has one, even if you can't actually see it. For example, light has a wavelength. It's just a very small wavelength, and our eyes cannot detect individual photons. Sound also has a physical wavelength, and specifically with sounds, I'm going to put 2 frequencies of sound up on the board. These are the lowest and highest frequencies of sound a human being can physically hear the moment they're born, or possibly the moment they first grow ears. And each of these frequencies has a corresponding wavelength. In general, for one type of wave, the bigger the frequency, the lower the wavelength, and vice versa. And we have one formula that helps us figure out that relationship. The speed of a wave equals its frequency times its wavelength. Speed of sound in air is always going to be 343.
Do we get that in questions when if we get like a wavelength question in the air?
Yes, this number will be given to you. It is considered to be a known constant. So if you need speed of sound in air for anything, it will be provided to you. But what this will tell us is, these are the highest and lowest frequencies we can hear. We can use this to find their corresponding wavelengths. And for the low, where's my calculator? Tiny, there you are. longest wavelength you can hear is 17.15 meters. That is that's about 56, 57 feet long. Meanwhile, the shortest wavelength you can hear is this tiny, about 1 centimeter long, and 2 centimeters long. And again, you can't really see sound waves, but these are the physical lengths of the waves themselves, and there's a pretty big difference here. Now, if I was to play this frequency of sound wave, this wavelength of sound wave, you wouldn't actually be able to hear it. This is what an infant might be able to hear, because your ears are at their sharpest the moment you're born, and every second your eardrums age after that point, this top number goes down. My max hearing is like 16,000 hertz. Yours is probably a little better than mine because you're younger than me. And hopefully you have not been blasting as much music into your ears with a headset. Although, no, that's going to be the same between all of us. So yours should be better than mine because you're younger. This number tends not to change though. So this should still be the longest wavelength of sound you can hear, and it's a physically long wave. It's so long that you don't really hear it so much as you feel it hit your body, because it's really long and it kind of forces the air to move out of the way to accommodate it. Which is why a car with puts a lot of bass. Bass is low frequency sound. These are bass tones. So the higher you got your bass cranked up, the more waves like this it's putting out. And when I hear bass, I don't really hear it in my ears. I feel it in my teeth. Sometimes if it's low enough, you can feel it physically hit your chest. So this refers to the physical size of the wave, and for sound uniquely, the bigger the wave is, the more you can actually feel it hit you. Does that help with your understanding?
Yeah, like I was in trouble with question 3 in the homework. Took me like three attempts to get the answer. I
Okay.
didn't understand why all of a sudden divided by 2 wasn't the distance.
Oh, okay. So dolphins rely on echolocation to survive in the ocean. Dolphins make a sound of this speed. At that frequency. This is the speed sound travels in water. Did you find trouble finding the wavelength?
No, that was okay, but like...
Okay. Now this, part 2, the reason you had to divide something by 2 is because this is an echo. And the quirk with an echo is the dolphin's going to make the sound. It's going to travel that distance and then travel back. So an echo covers the distance twice.
So if it would not be echo, if it would be lightning, then it would be just normal, no divided by 2.
Correct, because if you're trying to find the distance between you and lightning, lightning's going to produce the wave and it's going to travel from the source to you. It only covers that distance once. But if you make the wave and you're waiting for it to come back, it's going to do it twice. So I'm assuming the distance you found, you had to cut it in half?
Yeah.
Okay, yes, that is the issue here. This is a problem with echoes themselves. Dolphins do this, bats do this, any sonar detection system do this. Sonar uses sound waves and echoes to detect things. The SO in sonar actually stands for sound.
Can we do number 10?
And I know that's electric, I just forget which one. The eel. Okay. So an eel can output a very high voltage and a very high maximum current. This is the maximum that an electric eel can do. And this is after they've sat charging for a while, not doing anything else. But that's under ideal situations where they're not funneling that current through any sort of resistance. A snorkeler, the body of the snorkeler has this resistance. Everything resists, even your own body. Thankfully, your skin is designed as an insulator to keep you from shocking yourself. And this amount of current can kill a person. The current is dangerous. This is 500 milliamps, so that's about half an amp. Meaning that if this full current enters a human body, they might die. Don't go swimming near electric eels. Now, the first thing we're asked is, what is the maximum power that this eel can output at once? And there's lots of different equations for power. If you're looking at electrical power, I think the one that'll be most useful here is P equals IV. You take the maximum current that the eel can output, multiply it by the maximum voltage that the eel can output. Notice voltage of 570, current of 1. 1 times 570 is 570. Now, if the snorkeler is struck by the eel, what current will actually pass through their body? Now, the snorkeler has a resistance, meaning that this voltage can only squeeze so much current through this resistance. So you're going to have to use a different formula. V equals IR. Eel's voltage goes here, diver's resistance goes here. Solve for the actual current that passes through the human. The 1 amp is maximum, assuming no resistance. So since we're providing some resistance, we're going to reduce that by an amount. Excuse me. Now, based on these answers, we would get 0.83 amps as the current the human is exposed to. That is over half an amp. It's over 500 milliamps. So this is dangerous. And for the next part, how much power does the human receive from this? You want to take the actual current by the voltage and do P equal IV again. I think the way that eels build up their electricity is very similar to the way that our nerves fire.
Really?
It's just over their entire body, not just in the nervous system. You can create a bioelectricity by forcing charged ions to move from one place to another and carry electrons back and forth with them. And I think if they force enough ions to move quickly, that'll make a lot of electrons surge very quickly, which creates the current. I think that's meant. I know that's how it works in your nerves. I'm assuming the eel uses a similar method.
Yes.
Just because I don't know any other way to make bioelectricity. Does that help with this one?
Yeah.
Okay. I guess while I've got this homework pulled up, anything else from this homework you'd like us to address before I just run down the list of everything on the exam?
I'm good. Do you have any more questions?
I'm good.
Okay. So, if you were looking for, I have yet to fully compile the list in one place. I do apologize for that. But this test is going to contain basically everything. So right now I'm going up to the test 1 tab to look at the list of things from test 1. We're also going to look at the list of things from test 2. And And then I will also mention the things from last week that will be present. So, from the very beginning of the class, be able to do conversions, especially the metric system. I might include, like, King Henry died by drinking chocolate milk on the formula sheet, but you still need to be able to pretty quickly go between base and kilo and base. So metric scale, but there's other conversions too. A very common one is seconds to days and days to seconds. You don't have to use my railroad system as long as you have something that works for you, but I do like the railroad system, just setting it all out, doing it in a matter of steps. However it best works for you, be able to do unit conversions. Very specifically, I think a good example is one I had up fairly recently. Yeah, I did erase it in this last class. Your car very frequently tells you rotations per minute, RPM, but all of our formulas are designed to take radians per second. So, again, my railroad method, you want to cancel out rotations. So one rotation is equal to 2 pi radians. Cancel rotations. Minutes, 1 minute, has 60 seconds in it. And that will leave us with radians per second.
What's
This
that?
one comes up.
What's the name of this again?
Sorry?
What's the name of this 15 rotation per minute? What's the name?
This is a measure of angular velocity. So this is units of, like I say, a wheel spins and makes 15 full rotations in 1 minute. This is a measurement of angular speed, but most of our formulas are designed to take radians per second instead. I do not do this operator in my head. Okay, it was half a pi. So just converting between different units that tell you the same basic information. Be able to do that. And again, commonly be able to take something, switch it to kilo, or take kilo and switch it to base. Then we begin actually looking at movement by talking about displacement, velocity, and acceleration. The fantastic formulas. Those should be here. So be able to understand the relationships between these things and use these formulas to track the movement of an object. Bless you.
Thank you.
Difference between scalars and vectors. Vectors have a direction and scalars do not. That matters in terms of whether or not something is moving backwards or forwards. Then 1D and 2D motion. Know to keep axes separate. For example, on test 1, the answer key is here. Question 2, you can only add up things in the x-axis together, and you can only add up things in the y-axis together. So, understand whether or not two things given to you are in the same or different axes. Projectile motion is a very good example of a two-dimensional problem because something flies off of a cliff and it moves to the right as it also moves down. The main thing to do there is very specifically keep your axes separated. The vertical axis contains gravity. That's going to determine how long you're in the air. The horizontal axis contains only your horizontal launch speed. That tells you how far you go in this amount of time. All of our projectile motion questions look very similar. You're going to horizontally launch something off of a cliff or a building, etc. And you usually have to figure out how far away it will land. They all look very similarly. So review past ones, the ones on the test and the practice questions, to make sure you understand the setup, what they look like, and how to proceed.
Aren't those usually the third formula?
Correct.
Okay.
Except you need to do it once for each axis.
Right. That makes sense.
Do you use that formula also if you would like kick a football up in the air and down?
You can, yes. That formula can describe, you can use it to find where the ball is at any point in its arc. And you can use it to figure out how long it would take it to go up and come back down. So that formula 3 is the best formula to describe the motion of an object over time, whether or not it's accelerating. Formula 3 is a better version of Formula 1. From there, understand the principles of force. Force equals mass times acceleration. Force makes mass accelerate, but if an object is not accelerating, that means the forces on it add up to 0. There's lots of different forces that we've talked about, where you just apply a force directly. There's normal force, there's gravity, there's friction. Be aware of them, their main distinctive features, what direction they tend to point in, etc. Newton's laws of motion, there are 3 of them. Make sure on the practice test, I tend to write down, I'm thirsty again, sorry. On practice questions, I tend to ask you to write down the whole law, but on the test itself, what I'm going to ask you to do is pick from among a list of statements. Of these 5 statements, label which 3 of them are the laws of motion.
Like the last test?
Exactly. There's going to be one question for, out of all these, pick the laws of motion, a different question for, out of all these, pick the laws of thermodynamics. So at least be able to recognize them. They're very important. Work and power. To do work, you expend energy to perform a task. You exert force to make something move in a direction. Very specifically, remember that the force and the direction have to be in the same axis. And when you do work in a certain amount of time, that tells you power. Power equals work over time. That said, we've covered a lot of different formulas for power, and it does frustratingly share a variable with pressure. But power, whether or not it's manual work, whether or not it's electrical, whether or not anywhere the word power shows up, you're looking at energy used per time, no matter how else you calculate it. Even when it's thermal energy leaking through a wall, that's still energy per unit time. We talked about different forms of energy on the first test that only contained kinetic and gravitational potential. We have since expanded that list to include thermal. Know the different types of energy, what they typically do when an object has them. Because again, you cannot see the energy itself, only what an object does when it has that energy. Kinetic energy is the energy of movement. Gravitational potential is energy stored in your ability to fall. Thermal is energy that makes particles move around, like individual subatomic particles move around and collide, and eventually melt and evaporate. Momentum and impulse. Momentum is similar to energy, just a thing that matter can possess. Objects with momentum tend to not want to slow down. The more momentum something has, the harder it is to stop.
Did we have a momentum question or impulse in the test 1?
Yes. I do believe there was only one of them, though, I will admit. Test 1 has this one. This is the momentum and collisions question on test 1. And this is specifically asking about a collision. And in collisions, momentum is always conserved. which brings us to the next thing that was on that list, conservation of momentum in a collision. No matter what type of collision, of which there are two, momentum is conserved, so the total momentum that exists beforehand must exist afterwards. You add up the momentum of each object before and after, you can compare and contrast and try to figure out how fast everything is moving afterwards.
Did we have an impulse question on the first test?
We did not in retrospect.
Okay.
Admittedly, there was a lot of different things that I had to squeeze on that one test, and apparently not everything made it through.
Well, we need to know for the final one.
Yes. At least no momentum. At least know what momentum is, know how to do a collision question.
Right. And you want your collisions to be inelastic, right? In like the real world, like with cars and stuff.
Right, if you are in a collision, you want it to be inelastic. Because in an elastic collision, kinetic energy is conserved, which makes them more energetic and more chaotic. You do not want your car to bounce off of the other car. This one in number cars is bad for your neck and your car insurance and your bumper. And your brain. You get a concussion that way, or ignoring everything else. Momentum and impulse, collisions. Remember that for elastic collisions, kinetic energy is also conserved. That means you can also look at that type of collision from the perspective of total KE initial equals total KE final. There's also an additional formula that exists just for elastic collisions. V1 initial minus V2 initial equals V2 final minus V1 final. That one is a elastic only situation. The two things bounced off of each other and stayed in the same axis. Gravity. Remember that mass and the weight of an object are different things. Know that there are two ways to find the force of gravity on an object. One is with the big, long force of gravity equation. The other is to find the force of gravity of an object on Earth. Multiply its mass by 9.8. Make sure that is separate in your head from just a mass of an object. Weight is the force of gravity. Mass is how much matter there is. The last couple of things here, these three all have to do with the rotation chapter that we were on, which tie into...
Is that rotation on your right side on the table? What you read?
Yes, this is rotation.
Oh, so that's when the angular stuff
This is angular
starts?
stuff.
Okay.
Oh, wait, you mean on this list?
Yeah.
Yeah. All these bottom things here are all angular
Okay.
from chapter 4. Rotational motion is a synonym for angular motion that again uses the angular formulas that are the counterpart to the linear formulas. We also have the formulas to convert from one to the other. They are on the form of the sheet.
Okay.
Here they are. So these are the angular equivalent to the Fantastic Four. These are the conversions from one to the other. Understand the differences, that things are spinning now and that your units are radians. Understand the similarities and that all the logic is still the same. And know these exist and that radius is the conversion from one to the other. Additional angular related topics, we have angular acceleration. This is technically a linear acceleration in that it is measured in meters per second squared, but it does make things spin. It's linear because it points in a straight line to the center of the orbital form, but it is a part of making one object orbit another object.
Didn't we have like a merry-go-round question on one of our homeworks like that? Okay.
Also, on, say, test 1, for example, the big, hard whammy question on test 1 had centripetal force in it, but when an object is orbiting in space, gravity is what's acting as the centripetal force. So, in a question like this, both of them are here and they're equal to each other. This is probably the best, or at least most involved centripetal force question I've asked you, and it will probably continue to be the most advanced one that I asked you, that I will ask you. I like this question. I like space.
It's cool. Totally unrelated question. Have you seen 2001: Space Odyssey?
It's going to be a hit to my nerd cred, but not all the way through.
No? Okay.
I know at least the meme status of HAL 9000. I can't let you do that, David.
Oh, man. Yeah, I just watched it like a month ago.
Okay. When was it made? Several decades before the 2000s.
Oh, yeah.
It was a book first, wasn't it?
It probably was, I'm sure.
It's kind of the origin of the evil AI trope.
Yeah.
Without HAL
yeah.
9000, we would not have GLaDOS.
Was that before all the Terminator movies and stuff, too?
Absolutely. Terminator was like a Schwarzenegger in the 80s.
Oh, yeah, shoot. It didn't look that old when I watched it, but it was came out in 1968.
Yeah, it's definitely dated, but its visuals hold together better than you would have expected.
Yeah.
It's older than Star Wars.
Golly. I did not think it was that old when I watched it. Okay. Just blew my mind a little bit.
I mean, all of the older sci-fi assumed that by 2001 we'd be in space, like actually spacefaring people at this point.
Yeah.
Any work about the future always gets the dates wrong.
Yeah.
That's everything from test 1, and if you're looking at your first test, the answer key is down here in the exam tab to compare. Test 2. Test 2 is chapters 5 through 8. That was the 2 on pressure and the 2 on thermal energy and thermal processes. Know the definitions of pressure and density. Pressure is force over area. Density is mass divided by volume. These are important because density determines whether or not something will float in something else. And pressure, well, pressure is kind of the gist of chapters 5 and 6.
What was the formula for pressure again, for the definition?
The definition of pressure is force divided by surface area. When pressure is exerted on something, it is exerting a force over its entire surface area. So technically, if you are pushing against something with your hand, you are technically exerting a pressure. Like if I'm pushing